Great to be here. Thank you very much for having me. I was reflecting that I came to the first of these safety seminars and it was just pre-COVID and there were bushfires and you could barely see the Sydney Harbour Bridge and we didn't know what was to come. So it's great to be back under clearer skies. I'm going to talk about a project that I and colleagues have been undertaking with funding from ACARP and the US National Institute for Occupational Safety and Health. Now, the US is behind as far as automation in mining is concerned, and we were asked to look around the world and see what could be learned from the places that have installed automation in mining. So what lessons could be learned so that the US could be forewarned or perhaps forearmed. So of course, majority of automation in mining happens in Australia, most of it in the West, but there is sprinkling of other places around the world. So we spent some time in Chile and in Sweden, in Brazil, various places. So this is our best attempt at working out where automation's occurring. As you can see, Australia gets the gold medal by a long shot. In Australia, it's mostly, or the majority of installations are surface trucks. In Canada, which comes second, we're talking mostly underground metal LHDs. Now, I'm not going to show you lots of photos of trucks or dozers or loaders. You know what they look like. I'm going to show you some photos of what does automation look like from the perspective of the people involved in the system. Because that's my number one lesson, is that automation doesn't remove people from the system. Automation changes the roles that people in the system play. So here are some examples, or this is a Chilean control room for a surface haulage operation, and on the right there's some different interfaces from an alternate vendor. What's the first thing you get from looking at it from her perspective? What do you see? Or what's the thing you get? Screens, lots of information. So the role of the control room operator is one that's demanding. There's lots of information to be taken in, decisions to be made, communication with other people. We'll come back to that a bit along the line. So on the left here we have semi-autonomous dozer setup. So this they had this set up at the World Mining Congress in Brisbane, the exhibition centre. The dozer is being operated in central Queensland. Very impressive. On the right is autonomous drill rig. I like the little Xbox controller. That's an interesting way of thinking about it. So it's rather than with the dozer situation, semi-autonomous, there needs to be some teleop. So we provide, or they provide, a workstation that mimics that which is in the cab of the dozer. The drill rig, not very often used manually, but why do we need to replicate the controls? We can now use an Xbox controller. Talk about Gen Z or Alpha, maybe they're more familiar with that. But the only problem with that is that it does mean that you need to have different modes. So the controls do things in different modes. And whenever you have different modes, you have the potential for mode error. So there are things that creep in that need to be considered. So on the left here now, underground semi-autonomous loaders, and we'll come back and look at that in a little more detail later. On the right, autonomous longwall. Very impressive work that's been done. Now here, Australia's definitely leading the world. But again, what do you see? Lots of information, lots of video displays, lots of information for the people in the system to consider. Now, automation, in particularly haulage, has been going on for more than 10 years now. So we have a body of experience to try and understand what are the benefits. Because the other lesson I want to leave you with, or the other thought I want to leave you with, is that automation and removing people from hazards, that is the only way that we'll get a step change in safety and health. Everything else is tinkering around the edges in my mind. So removing people from hazards through automation or teleop, that's the way we've got to go. It's not easy necessarily. But we have had experience, and I'm going to steal a slide from a presentation that was given by John McGarr 10 years ago. So John was responsible, he was head of innovation at Rio Tinto at the time that the autonomous haulage was being kicked off. And he gave a presentation reflecting on what it took to successfully implement those projects. And the slide I want to focus on is this one, because it's easy for me, I'm Professor of Human Factors, it's in my title, you expect me to say human factors is important. But this is from a different viewpoint. This is from an engineer responsible for innovation, saying that underpinning the technology lies the critical world of the human. This is where the implementation of technology will be done well or not. The technology bit, that's the easy bit. How do you make it work for people? That's the harder bit. Anybody enjoy checking in at the hotel using their lovely screen where you have to reach out, and especially if you've got a very long name and you make typos, you get a sore shoulder just checking in. That's not designing technology to take people into account. The things that John said to think about very carefully. Safety, number one. If you don't get the safety right, nothing else matters. Now, human systems interaction. Now, I think he meant human systems integration, and we'll come back to at the end of the presentation what that means. And then the change does need to be socially acceptable. So now I've said that automation is safer. It's easy to say, logically it makes sense, but what's the evidence? There are some data available. Now, as I said, we've had 10 years of experience with automated surface haulage. So these data are from Rio Tinto comparing manual operations or manual haulage operations with autonomous haulage operations in terms of near misses per million truck hours. Dramatic difference. I've circled the bars that are relevant, the haul truck bars. Huge difference. Now, the researcher in me says, yes, but all those autonomous operations are in Australia and the manual ones are generally not. So it's not just, there's not just autonomous that's different. That's true. However, that difference is so stark that I'm willing to accept that as being an indication that there is some safety benefits of autonomous haulage. And there are also some data from BHP. These are now all Australian data comparing Jimble Bar, where they have autonomous haulage, versus the average of conventional operations. Again, the difference is stark. Now we're talking about safety events, however defined. So, to recap, automation is where you'll get huge safety benefits. There is evidence that it's effective, but I don't want you to think that there are no potential problems. There are some along the way, and we'll touch on some of those now. One general thing that can go wrong is that the people in the system can lose situation awareness. And so this is the only example of a collision which resulted in injury. Now, not time lost injury, very important if you count stats that way. It wasn't a time lost injury, but there was still a minor injuries. The issue was that the manually operated water car was driving in opposite direction to an autonomous haul truck. The truck was tasked with turning around at an unusual place. This wasn't somewhere they normally turned around, so the manual operator of the water cart didn't notice they were turning until it was too late. Laws of physics still apply. Everybody can jam their brakes on at that point, but you can't prevent a collision. But the interesting thing was there is a system provided within the manual truck which was supposed to provide information about what the autonomous truck was doing. So there is an awareness system, they call it, but it wasn't effective. Why not? So this photo is taken from the back of a light vehicle. Those lights you can see coming towards us is an autonomous haul truck, and the driver said to us, "Oh, he's going to turn left." Well, there's no he. So there's interesting personification going on. Perhaps it helps to trust the computer if I think of it as a he. But the other thing, I was looking at the screen thinking, well, how the hell do you know that? And how can you tell that quickly enough to make decisions? Now, we were stationary, so it wasn't particularly a rush to make a decision. But if you put yourself in the shoes of the driver of the water cart, they've got to make if they were going to avoid that collision, there needed to be a decision made quickly. They didn't get the information in time. So it's not a failure of the driver, it's a failure of the system to provide a means of maintaining situation awareness. So here's some other examples of the screens provided. And from a human factors point of view, I'm going to say I think there's room for improvement in these screens. Now, there are other examples of similar types of incidents, just to reinforce that this wasn't a once-off. You read that for a moment and I'll get some water. I particularly like the last one. So an investigation found that the light vehicle driver lost situation awareness. Okay, so they're really recognising the issue here, having been distracted by focusing on the side awareness screen. Hang on, that was the screen that was supposed to be helping you maintain situation awareness. So there's an issue there, and that's one general issue. Now, you'll be familiar with this collision between an autonomous, semi-autonomous dozer and an excavator. There were lots of things that went wrong, but I want to just take the focus on this image from the report. If you look in the bottom right of that screen, there's the video available to the operator at just immediately prior to the collision. The point I want to make is that providing a video display doesn't necessarily mean that someone's going to take that information in, understand it, be able to make a decision in time. Because at that moment, the operator was focusing on another dozer altogether that had a different problem. So I'm sure when the design of this system was undertaken, the thought was, well, we'll give them the video display, then they'll be able to maintain awareness of situation awareness of what's going on all the time. So that's not sufficient. The image on the right there is my understanding of what the text says. Now, this could be a loss of situation awareness. So the light vehicle coming through the intersection should have priority rules applied, should have given way to the autonomous truck turning right in front. Could have just been, oh, well, I didn't notice it was going to turn right. But the fact that there was no report afterwards when it must have been apparent what had happened, I suspect this is an example now we're getting into overtrust. So we overtrust technology all the time. Have you ever followed your GPS navigator and then found yourself on a dirt road taking a shortcut? Okay, that's overtrust. So it's a normal thing to do. Once you like the technology works for you, you start to trust it, you can tip over into overtrust. So I suspect that's what's happened here, is that I know that truck will stop for me if I drive through in front of it. It's got all those fancy sensors, it'll stop. So I'm going to take advantage of that because I'm in a hurry because what I'm doing is important. That's a risk. That's human nature. It's one of the things that worries me about putting technology on underground vehicles that will stop proximity detection interlocked with brakes, because then people working around that equipment are likely to think, oh, well, it's going to stop for me. I don't need to perhaps be quite as careful about walking out in front of it. Sometimes the things that go wrong are not quite as simple. So this one, where there was a communication disruption, but there was a misunderstanding about what vehicles had lost communication. Pedestrians were dispatched to recover the autonomous trucks, and then the communication was restored to the trucks, and they both started off moving again, whilst in one case someone was about to climb on board. So this is a situation where starting to get into some complex interactions. And one of the things we'll talk about in a moment is when you're doing the analysis, that it's not enough to say what happens if something goes wrong, how do we prevent it going wrong? Sometimes it's more complex than that. I said we'd return to the operators of control rooms and the workload. This is one of the potential problems with lumping more and more things on people in the control room. So we didn't spend a long time in any particular control room, but our impressions were that the workloads were high. There have been other researchers who have spent long periods of time in place, so there's some quotes from their reports. We're talking about here really high workloads and things that, so Todd Pascoe's quote from a control room operator, previously you had 40 drivers who could think about it. Now you've got one looking after 25 trucks, planning all the work. It's constant churn, it just doesn't stop. It's relentless. And Peter Chergwin talks about the controllers who thought their life was going to be made easier by autonomous operations, but the experience was the opposite. So there's a real risk with adding to the workload of controllers, and that needs to be considered. The other thing is that if you are embarking on this, one of the lessons I think was learned was that train twice as many people as you think you're going to need, because inevitably there will be a bigger churn than you expect, or they'll be poached, or they'll decide they didn't want to do that after all, and then it gets into this negative spiral. We can't afford to release people for training because we haven't got enough people. So those are a selection of what we termed credible failure modes, the ways that things can go wrong during the implementation of automation. But I want to not say that this is, a bad thing. These are the issues you have to look out for, but this is certainly the way to go forward. So I also want to now switch to a positive example. A few years ago, we did a case study describing the implementation of semi-autonomous loading at North Parks. I'm sure many of you are familiar with what happens there, but I'll recap briefly for those who are not. So there are operators in a surface control room that load ore via teleop. Then the loader takes itself off to the dump point, dumps and then returns to the next draw point, all autonomously. So each operator in the control room is responsible for 3 loaders. They have controls that used for the teleop that mimic the underground loader. They monitor again, there's lots of screens, we'll see in a moment. There's lots of information. They make decisions in response to events. So the roadway deteriorates, they change the speed. There's the need to go to a different draw point, they'll do that. There's definitely improvements in safety. All those health risks that people in underground loaders are exposed to are no longer there. Dust, vibration, risk of, one site had people in full face helmets because not North Parks, because sometimes the loader would catch the rib and slam people forward into the deck. What's the word I'm looking for? Anyway, all those risks are gone. So there's definitely safety improvements. Also 23% improvement in productivity, and mostly that came about through being able to continue to load through blasting. So it looks like, again, lots of screens. The bit I want to focus on mostly is how did they get there? Because this was the 3rd attempt. It's not easy to achieve such a big change. But on the 3rd attempt, there was a strategy, a deliberate strategy employed, and these, I think, are the highlights of the way that they went about it. It was successful. So everybody who was involved, everybody impacted by the change was involved in discussions and understanding how it was going to happen. The feedback loop between the operators and the designers was very close. The designers, the software designers, were on site during that commissioning. That was critical to get that quick feedback loop. The interface design really focused on allowing the operators to maintain awareness of the situation continuously. And I think having to intervene once a cycle to do the loading teleop paradoxically has an effect that maintains awareness of the operators. They're checking in once a cycle with what each loader is up to. There was flexibility that was provided. So rather than the designers assuming they knew how the equipment could be best operated, provide as much flexibility as possible to the operators and empower them to make changes and take action. One of the decisions that was made was how many loaders should each operator be responsible for. And that decision was made by the operators. And then they were taking advantage of new possibilities that arose. So there were unintended benefits of the system that were encountered along the way. So that process that they went through is, in a sense, human systems integration. I didn't know that's what they were doing, but there is a branch of systems engineering called human systems integration. It arose out of US defence from a series of disasters in terms of acquiring new technology, things that led to fratricide events. So, for example, someone in the field using a GPS to highlight a location that they wanted, where enemy was located, and inadvertently putting in their own location and causing fratricide events. That's an example where the interface was not designed for the use of people. And so there was a concerted effort to work out how do we go about better designing technology to take people into account. So, it's a branch of systems engineering. The goal there is to optimise human-related considerations during system design, development, test, and so on. So the relevant Department of Defence instruction is there. We need to ensure that the system's designed to be operated, maintained, and supported. NASA does it pretty well. They've got some very good documentation, adjusted slightly for their civilian use, but still maintaining the same core principles. The rail industry has again also adapted it slightly. The US rail calls it human systems integration. Still in Australia, we call it human factors integration. Slightly different nuance in the rail industry. I've put the photo of Rio Tinto's autonomous heavy haul train there, so the largest robot in the world. The interesting thing about the train is that took much, much, much longer to get operational than the autonomous haulage. And you might think, on the face of it, the train runs on tracks. Surely that's a lot easier to automate than a truck. But it turns out the huge difference is that the trucks all run on an enclosed mine site where we know where everybody is. Trains have to run across public land, and more importantly, they have a regulator which has in their regulations that we need to demonstrate how human systems integration has been achieved. So that took a lot longer. So I've adapted the framework of human systems integration from those other industries and tried to put it into a mining-related context, or adapt it for mining. There is a cycle from requirements and analysis to working out what the system needs to do, through the design and development to testing and evaluation. Throughout that cycle, each of the domains listed need to be addressed. Now, the domains interact. It's not a matter of looking at one and doing them in sequence. You need to consider them all at the same time. So the first domain might be questions about what people do you need in the system? Remember that the system doesn't exclude people. There are people in that system. So the first question you might be, well, how many are there going to be, and what are the roles that we're going to need to operate and to maintain this new system? The question that follows from that is, well, where are we going to find these people? Who are they going to be? What are their characteristics? So from the North Park's point of view, the decision was straightforward. We'll take the people who have been accustomed to operating loaders manually, and we'll bring them into the control room. We're going to do that. And that has some advantages because those people already understand the system intimately. They already have experience with manual operation, so the teleop will be relatively straightforward. And so that impacts on decisions about the training that's going to be required. Of course, that's not static, because in the future there will not be people who have experience with manual operation. So our training will need to change in our methods of competency assessment. Now that's not insurmountable. Virtual reality is the logical method for doing that. But it's also demonstrating, as well as something that happens throughout requirements, design and evaluation, it's also something that it's not static, it changes over time as well. The human factors engineering part is how do we get the interface right? How do we make sure that the workload of people is not overloaded? People are not overloaded. And there are techniques for that. So human-in-the-loop simulation, for example, is a good way of trying to work out what the workload might be before we've actually built the thing. And they interact because it depends on the people you have and how much training you give them, or the other way around. If you get the interface right, you can reduce the amount of training you need. So they interact. Now the safety bit, safety is a subset of human systems integration. That sounds strange, surely safety is at the top, but not really, because it's all about people. And if you don't have people, then it's not about safety. It might be about loss prevention, but it's not about safety. So safety is a subset of the bigger human systems integration piece. Now the techniques here, you're familiar with many of them, conventional LOPA and FMEA, all those good things, but also task-based risk assessment, looking at it from the point of view of the tasks that people do. And then the other one that might not be so familiar is systems theoretic process analysis. This is a method which says most of the other methods will start from the assumption that, okay, what can go wrong? How do we prevent something bad from happening as a consequence? STPA says, what can go wrong even though everything functions as intended? Because if we have a sufficiently complex system, that's a possibility. I've got functional safety in there, but to me that's a very, very small part. There are potential health effects. So again, that workload overload has potential health consequences for people. The other sort of health things you might think about, well, if we're putting someone in a control room 12 hours a day sitting, maybe there's some health effects there. Those are not new. So to expand out what's in requirements and analysis, so this is when you're thinking about what's the initial concept of operations. And then you need to define at that point, what are the requirements going to be for the information that people get, where are they going to get that information from, how are we going to select and train people. That all should be done at requirements. So notice training sometimes gets left to the end. We've got a system, we need some people to operate it. Oh, how are we going to train them? Training needs to be considered right at the beginning. And then we've got through our design and development. It's an iterative phase, you're never going to get it right first time. This is where your software and interfaces are critical, and the training and more documentation. Then the last stage, this testing and evaluation, this is where you're making sure that everything has achieved what was intended to achieve. And there's a nice little phrase there, human engineering discrepancy resolution. Any clues, any ideas what that might mean? It means what do we do when we haven't been able to achieve what we had described was required, when there's a discrepancy in terms of how people can operate or should operate. And that can be a difficult conversation, but it's better to at least acknowledge and identify discrepancies or deficiencies in the design rather than try and paper them over and ignore them. So it might mean, okay, well, there's going to be more training required. It might be that we need to go back and redesign something, but needs to be identified. How am I going for time? I can't quite see. The last thing I want to leave you with, almost the last thing, is the idea that you're familiar with technical readiness levels, technology readiness levels. There are parallel human readiness levels. And one way of thinking about human systems integration is it's a way of ensuring that we meet a required level of human readiness that matches the technology readiness of the system. So the take-home message is that any technology implementation, doesn't have to be automation, but any technology implementation requires a human systems integration plan. It's going to be a collaboration between a vendor and a purchaser. The vendor can't do it on their own. Remember that critical part of the North Park's success was the close feedback loops between the operators and the designers. That was a critical part of that success. So the human systems integration can't be done by the technology vendor alone. They need cooperation from site, they need participation from people on site. But it needs to address all of those domains throughout the whole analysis, design and evaluation. So it's not something that happens on a single occasion, a single risk assessment. It's something that has to be embedded within the whole procurement process. So part of that procurement is, to a vendor, from my point of view, that should be, what is your plan for human systems integration? How are we going to be involved? What skills do you have? Who in your organisation is going to be doing this? How are they going to do it? What are the milestones? Needs a plan. So we have provided a white paper which summarises the research. And there is a book coming out next year. I'm sure it'll be a bestseller, but so look out for that. Okay, I think that's me.